Today we have Dr. Sebastian Heinz, who's coming from the University of Wisconsin. I first met Sebastian when he was a grad student working for Mitch Begelman at the University of Colorado way back in the 90s. Working on similar stuff, as I recall, right?
Yeah, it started that way.
Started off with theoretical modeling of jets and their interactions with external media like clusters. Sebastian then went on to a postdoc at Max Planck, working with Rashid Sanyaev of Shakir Sanyaev disk fame, which Max Planck was the
Astrophysics, that's the theory.
That's in Garking, that's right, okay. And then from there you had an Einstein Fellowship, right?
It was Chandra at the time, but yeah.
Yes, okay. It was a Chandra Fellowship, later became an Einstein Fellowship, later became a Hubble Fellowship, now it is these days, at MIT, where we reconnected again. And then from there, he went on to faculty at the University of Wisconsin, Department of Astronomy, including a stint as chair, which you're thankfully now free of. And so now, aside from working on jets and their interactions with external media, which we'll hear about today, Sebastian also has a sideline working in physics of dust and dust scattering halos in front of X-ray sources. So if you go online, you can find a very lovely picture of the dust scattering halos being illuminated by source SX1 in the background. And that's a nice thing to go look at. And I think you can check it in later on today about that. So without further ado, Sebastian.
Yeah. Thanks, Mike. It's great to be here. This is my first sort of in-person scientific seminar since the pandemic. Giving public talks in person, but not. So this is it's great to be here and to be able to do this. And thanks for the invitation, Mike. So before I start, I want to highlight a few of the collaborators in particular that are listed on the screen here. Students. Let's see if this works. Yihao Chen here, who did a lot of this work. And then Jennifer Stafford, who is working on. So maybe I will. That's Jennifer Stafford here, who's working on this now, and then Tara Elon, who's in the top right corner. Let's start. Okay, so I'll talk to you about a topic that I've been working on for a long time, as Mike said, and there are two things that I need to introduce you to. Most of you probably already heard about this, these kinds of astrophysical objects that I'll talk about. The first are what we call radio galaxies or jets. So these are very powerful outflows launched by supermassive black holes in the centers of galaxies, and this is a famous image of the radio galaxy Cygnus A. So you have a black hole, supermassive black hole in the center of this image, and it launches two very collimated, magnetized relativistic outflows in opposite directions, propagating away from the black hole. And on very large scales, these jets terminate as they interact with the medium that they propagate into, and as they terminate, they deposit the plasma that was flowing down the jet along the way, filling out these large lobes, as we call them, of synchrotron emitting plasma. So this is relativistic particles in magnetic fields deposited in these large scale lobes. And so this image is about 400,000 light years across. So this is a large structure, much larger than the host galaxy. And in fact, this radio galaxy, this whole structure we call a radio galaxy, is embedded in a galaxy cluster. And it fills these radio lobes, these cavities, inside the medium of the cluster. So what's the cluster? Here is a famous image of Abell 2022-18, which is a lensing cluster. It's a galaxy cluster of galaxies with hundreds to thousands of galaxies comprising the cluster in the visible light. So what you see here is a visible image with beautiful lensed arcs of the background galaxy by this cluster. Most of the mass in this cluster is dark matter, and we can see this in the lensing strength. But most of the gas in this cluster is not in the stars at all. It's in the X-ray emitting plasma that fills the space in between galaxies. We call it the intracluster medium, and it has most of the mass gas in this cluster, and it emits in X-rays. because it is tens of millions of degrees hot. And so here's an image of a different cluster, the Coma Cluster, another famous cluster taken by the Chandra X-ray telescope. You can see this X-ray emitting plasma filling the space between the galaxies. And so the typical thing you say about clusters when you write a proposal or paper is clusters are the largest virial structures in the universe. So they are the tips of the iceberg of structure formation. When structure collapses in the universe, it collapses onto filaments. Filaments condense into galaxies, and galaxies then condense and fall into these galaxy clusters. So they are the largest, densest regions in interstellar space. There are two types of clusters that we distinguish based on the X-ray emission we see from them. There are what we call cool core clusters on the left, and they're non-cool core clusters, which is just kind of an uninspired name, but that's anything that's not a cool core cluster on the right. And what you see here is a histogram of the surface brightness in X-rays, the intensity, how much X-ray flux you get per solid angle. And a cool core cluster on the left, as you can see, is much, much brighter in the center than a non-cool core cluster, by an order of magnitude or more. And why is that? Well, the reason for that is that the gas in this cool core cluster has had time to condense, to cool to lower temperatures. And because the emission goes like the square of the density, these are much, much brighter. They're much denser in the center, and because of that, they cool very quickly. And on the right-hand side, the gas is all hot, 7 keV or so, 70 million Kelvin. And this actually presented a problem when this first was discovered, because the cooling time for the gas in the center is much, much shorter than the age of the cluster. And so that would imply that this gas should all condense, it should all cool to very low temperatures, form lots of stars, thousands of solar masses of star formation, which is not observed. We don't see this massive star formation. And in fact, we don't even see this gas at low temperatures. And this was initially called the cooling flow problem. And I will talk about this problem today. So here's another cluster. This is now a cool core cluster, the Perseus cluster, which is the topic of discussion for today. So I'm going to talk mostly about this particular cluster because it is the best studied cool core cluster. And it's relatively close, it's very bright, and we have a huge trove of observations of this cluster. So what you see here is an overlay of optical in white, X-ray in sort of bluish purple, and radio in magenta. And all of these structures are relevant. Overlaid, also you see these dark lanes. This is actually a foreground galaxy that you see in X-ray absorption. This is a real X-ray of that galaxy, like you would go to the doctor and see arm absorption. It's an X-ray of the galaxy, but I want to talk about the background emission you see here in diffuse light. And what you see is that this X-ray emission here in blue is bright, sort of on this scale, but there's actually a dark region in the center. And that dark region is filled with radio emission. That magenta radio emission fills these two dark spots in the X-rays. The radio emission comes from a radio galaxy. So this is a jet launched by the supermassive black hole in the center of this cluster. This is another image, or two images of the same cluster. Again, Chandra X-ray image on the left. There you see very clearly these two dark regions in X-rays. Right? These are cavities. There's missing gas. Gas has been removed from this. And there's actually larger cavities on these kinds of scales. And so this is just the intensity, the brightness. But on the right-hand side, you see a temperature map from Newton telescope. And so blue is cold in this map, and red is hot. And you notice immediately that the center of this cool core cluster is indeed cool. Right? It's roughly 2 kiloelectron volts, and out here it's about 7. So much hotter. So this is a classic cool core cluster. But there's a problem, as I said, with these cool core clusters, because the gas in the center doesn't actually cool as we would expect theoretically. So this is an X-ray spectrum of a cool core cluster. And this is now in wavelength. What you see in black here is the data. This is taken again by the XMM Newton telescope. So data in black, best fit model of thermal gas in red, of the cooling flow model, and then the expectation in green. Right? If this were actually a cooling flow that were to allow the gas to cool all the way to the temperatures it wants to cool, you would see the green spectrum, and you don't. Right? There's missing line emission. In particular here, some of the iron lines are just missing. And that means that the gas that would emit lines at this temperature is not there. And that gas would be a hold temperatures below about keV. And so we don't see this cold gas. We see gas that cools, but it cools only to about 2 keV. It stops. So something prevents the cold gas from cooling even further. And so this is the cooling flow problem. Initially, when people saw this, they thought, well, maybe it's not a cooling flow problem. Maybe we just call this cool core because this isn't actually a cooling flow. The gas doesn't cool all the way down to zero temperature, basically. But it's still a problem. And that means that we have to allow the gas to cool to the temperatures to make the lines we observe, but then we have to stop it from cooling. So there has to be an energy input into this cluster that provides enough heat to keep the gas from cooling further. And so we have to provide about a trillion solar luminosities in heating power to this gas constantly. And so that's the energy released typically, for example, by a supermassive black hole. So when this first became apparent, people were looking for possible heat sources to solve this problem. How can we keep this gas from cooling all the way to low temperatures? And three mechanisms were proposed. So the first, in fact, was conduction. And I'll talk about conduction today. Because you have a heat bath, right? You have very hot gas, and then you have cold gas in the center. In principle, it would be possible to conduct heat from the heat bath, the cluster exterior to the interior. And we'll talk about why that was rejected. Another possible source of energy for these clusters is simple dynamical energy. So, for example, if two clusters collide, they can heat by simple shock heating the gas in clusters. And in fact, that's what makes non-cool core clusters hot. Non-cool core clusters are not relaxed objects. They had a recent interaction with another object, and that has shock heated the gas back to the virial temperature of the cluster. But this is obviously not an interacting system. Cool core clusters are relaxed, so they haven't had a recent interaction. So that's not something that has the ability to heat them. And it's very difficult to explain why you can magically arrange an interaction with a neighbor just when you need heat. So there isn't a feedback switch. There isn't a mechanism to turn the heating on when you need it. So this is also rejected. And so that leaves the third hypothesis, which is that you actually provide heat by the central black hole through the inflation of these radio cavities, these bubbles. And that's the canonical picture. So the canonical picture today is that cool core clusters are heated by energy released by black holes in these cavities, mechanical energy, that is then somehow transferred to heat. So conduction was initially suggested, and I'll just briefly talk about why it was rejected. The conductive heat flux is given by the temperature gradient and the conduction coefficient. And so you notice it's proportional to the temperature gradient. If this is a temperature map, then on the left-hand side, you have a small temperature gradient, less conduction. On the right-hand side, you have large temperature gradient, more conduction. And the conduction is strongest where the temperature gradient is largest. So the closer together you bring hot and cold gas, the more efficient conduction becomes. And then it depends, so that's sort of depicted by these arrows. And then it's also proportional. Question? Okay. It's also proportional to the conduction coefficient, which in the sort of canonical plasma physics approach to evaluating these coefficients for astrophysical plasmas is proportional to the 5/2 power of the temperature. It's pretty strong dependence. And so conduction is also more efficient when the gas is hot. Okay, so again, if you have hotter gas, you get more conduction. And then the heating rate is just the divergence of the heat flux. Right, so that's the expression for how much heating you get locally in your pocket of gas. So you don't just need a heat flux, you actually need a divergence of heat flux so that you deposit or withdraw energy from source gas. So that's the physics of heat conduction. It's obviously well understood basic physics. And based on just calculating the conduction coefficient and the temperature gradient in a cluster like this, right? You can see this is a huge distance. Right, this would be hundreds of thousands of light years. The conduction rate is simply too slow to provide the amount of heat flux into the center to provide heat. And in addition, in the mid-2000s, people were calculating the stability or the dynamical and kinetic stability of these systems under heat flux in the presence of magnetic fields, even small magnetic fields, Guy fields. And what they found is that there's an instability that's driven by the heat flux. Right? There's free energy in the temperature gradient that you can tap into, and it drives an instability called the heat flux driven buoyancy instability. That's a mouthful. And what that does is it actually turns magnetic fields that are aligned with the temperature gradient perpendicular to the temperature gradient, and that further shuts off conduction. Only along, only in the direction of the rotation. So it doesn't work if you just have hot and cold plasma next to each other, but if you have a temperature gradient, we have a stably stratified atmosphere, conducting heat along the temperature gradient turns the conduction off. So conduction was widely rejected as a mechanism in clustering. Yeah.
Can I ask you a question? So do we know what type of gas it is, and does it matter if it's ionized or neutral or atomic, molecular?
Yeah, we do, yeah. So this is all ionized gas, right? This is 10 million degree, 20, 30 million degree plasma. So purely, it's entirely ionized up to, depending on what the temperature is, the different species of iron, some higher, ionization states of oxygen and heavier metals exist, of course. But helium and hydrogen are fully ionized. It's fairly straightforward to calculate the conduction because it's just electron conduction.
I have one more question.
So this is kind of equivalent to why you have a long handle on your stovetop, right? You want to make a long distance between the heat source and your hand, and that efficiently turns off conduction. So that's the picture to have in mind, right? It's this large distance between the heat source and where you need heat. Okay, so those have basically been ruled out. So that leaves this question of, how do we heat, in the presence of radio galaxies, which is what my group is studying. So back to this picture of energy released from the center of the cluster, where you have the most massive galaxy right here. So the galaxy is probably about this big. In this picture, just to give you a scale, Milky Way would be about this big. This is in a massive elliptical galaxy that's probably bigger, but just for scale. And so you shoot out energy, plasma with strong magnetic fields, relativistic particles at close to the speed of light, 99% speed of light or faster, into interstellar space, where it then inflates these cavities. And the amount of energy released by an object like this is certainly more than all the stars in the galaxy and host galaxies together. And in principle, the amount of energy released is actually comparable to the cooling rate in clusters. And I'll show you a more detailed plot of that. So the picture here is we have a massive black hole in the center. It releases energy in sort of bipolar direction, although the direction might change, and that inflates these cavities. And by moving gas around, by injecting kinetic energy, you can then heat the gas. So this is a really well-established picture for cool core clusters. And in fact, every single cool core cluster that we know has one of these radio galaxies in the center. Right, so here is a sort of a smattering of different cool core clusters in X-rays and radio. Sometimes there's some optical overlaid, but what you see here, this is again the Perseus cluster, but in every single system we see these cavities, so harder to see in some of these, but they're all here. And the cavities are filled with some radio emission injected by the central black hole. And on the right-hand side in this plot here, you actually see on the x-axis here, the cooling luminosity of the cluster, the core of the cluster, which is the amount of energy or the power that you have to provide if you want to keep this cluster hot. Right, so that's the amount of energy you need. And on the y-axis is the power that the black hole provides into the cavity. So how much energy is released by the black hole is plotted here, and then on the x-axis is how much you need. And so here are different systems from small groups to very large clusters, very powerful cool core clusters. And you notice that there's a trend. There could be some biases that make this more pronounced than it actually is, but for the most part, you see that there is a relation between how much power the black hole releases and how much power is required to heat the cluster. Now, these dotted lines here are different conversion efficiencies of the energy that's provided by the black hole into how much energy is actually positive. So the way that we calculate the energy in these bubbles, or the energy injected by the black hole, is just to make a simple back of the envelope argument, basically saying the total amount of mechanical energy to inflate a bubble, the work you have to do on the environment is just PV. Right? So P is the pressure of the environment. If you want to inflate a bubble with volume V, the amount of energy required is roughly PV. But that's not all the energy, because the bubble itself also contains internal energy once you've inflated it. Because this is a relativistic gas, the amount of energy, the internal energy is three times PV. So 3 PV is you get for a relativistic gas if you have a monotone ideal gas. And so the total amount of energy available is 4 PV. 1 PV for the work done, and then 3 PV for the energy remaining inside the bubble. So that's the middle line here. And then, there's another line, so 16 PV, so that's certainly more than you have. And you notice that there are a number of clusters that lie to the right of this line. And so there are some systems where the amount of energy injected by the jet itself does not appear to be enough. So that presents a question, right? Even the ones that are slightly to the left of this line, you have to have a very large efficiency of turning the amount of energy that's released by the black hole into heat. Because the work you've done on the environment by inflating the bubble isn't necessarily turned into heat, right? If you do this work lifting up some gas, that's gravitational potential energy, right? If you induce a pressure wave, that's actually not dissipative. You've just induced fluctuation that will propagate through the cluster and disappear, right? It will heat some, maybe it will dissipate on some larger scales, and that's not useful. So in fact, this is a pretty tight energy argument. And the question is, what efficiency do we need for this heating? And so to study this, we do MHD simulations of jet inflation in clusters of galaxies. We do this on computers like this. This is the Stampede 2 supercomputer in Texas, where we use about 11 million CPU hours for these kinds of simulations. And we have more time coming up. So this is a fantastic facility. If you need computing time, exceed is going away, but it's going to be replaced by Access, which is the new NSF acronym for whatever supercomputing infrastructure they have with the computers that listen. Okay, so here is an image of one of our simulations. Again, students working on this listed here. And what I show here is actually a 3D render of the magnetic field in the radial lobes inflated by the jet. So we do full MHD simulations. The jet is coming out in this direction here, and then this is the spaghetti here is the magnetic fields, field lines, and then over here is just a volume render of the tracer fluid that we use to track where the jet is inflating the bubble. On the bottom here is a slice through the magnetic field through the center of the simulation. On the back here is just a projected radial. So this is what it would look like if we were to observe it, and it actually looks pretty similar to the structures we see in these clusters. So the simulations themselves use the Flash code. It's an MHD code that we've modified heavily to do this. We fully resolve the MHD structure of the jets just to make sure we do justice to the physics of the jets themselves. Beta here is the plasma beta, so it's the ratio of gas pressure to magnetic pressure, and we set that equal to 1. So they are roughly an equipartition. That means roughly the same amount of energy in magnetic fields and gas pressure in these jets. They're not fully relativistic simulations. I just have to say that now because this is numerically extremely challenging already. And so these are jets that move at 0.1 to 0.2 times the speed of light. And that's not appropriate for the jets themselves, but it is appropriate for when they interact with the jet. We use Lagrangian tracer particles. So that's particles that are embedded into the fluid that track where the gas is moving, and that will become important in just a little bit. We solve the particle transport equation implicitly, so that allows us to calculate things like synchrotron emission accurately. And just for reference, the resolution of our simulations is 30 parsecs. So that's 100 light years, and the cluster itself, is hundreds of thousands of light years. So we have a very large dynamic range to deal with, and the way we do this is using adaptive mesh refinement. So the code doesn't resolve the entire cluster the same everywhere. It resolves the fluid where it needs to resolve it because we need to resolve the dynamics, but it doesn't spend time or energy or resources on regions where it's not necessary. And what we simulate is the process cluster. So this is an overview of the simulations, and then just for a reference, we inject jets that are magnetized in different ways. Some are magnetized with a helical magnetic field in the jet. Some are purely toroidal loops. Some are colloidal, just to investigate what the dynamical effects of that are. So here just slices through the simulation of different configurations. I'm not going to talk about this in any detail today. You notice that they look slightly different in terms of the overall morphology. These are all the same age with the same power. And there are differences that I don't want to go into detail here today, but we can talk about it in session questions. And so here's a movie of one of the simulations that shows the jet, and I will explain why the jet wiggles in just a second. So the black hole is in the center, and it injects these jets, and the jets propagate into the interstellar medium or galactic intercluster medium, and then they deflate these radials, which look pretty much exactly like the image of Sigma state, for example, that I showed you. So that seems to work pretty well to describe the overall dynamics of these sources. You notice that the jets wiggle, right? And that's actually something that we impose on the simulation. And if we were to just have a straight jet propagate straight down one direction only, it would inflate a very narrow cigar-shaped cocoon, which is not what we observe. So this is a well-known long-studied problem in jet interaction. It's called the Dentistrol Effect. It basically states that we require some form of instabilities or change in the jet axis by a little bit to distribute the momentum that's transported down the jet over a larger area so that you inflate something that looks like a radio galaxy rather than a cigar. So we do this too, other people do it too. There are questions whether this can be mitigated to some degree by relativistic effects, but we don't have the ability to do this in full relativity for the time scales we need to do, just to answer that question. So here is another movie now with the jets actually taken out, just to show you the dynamics of the bubble that we inflate at the cavity. And so this runs for longer. This is, you can see the time scale here, millions of years. I think the axes are cut off, but these are kiloparsecs. So, so I'll just do this one again, just for scale, right? So this is 60 kiloparsecs, so it's 120 kiloparsecs in height and about 240 kiloparsecs in width. So that's, you multiply that by 3, and that's how many hundreds of thousands of light years you have in this. So initially the jet is on, and then at some point we turn it off, just to let the structure evolve and see what happens. Because we know that these jets in clusters are episodic, and so we study what happens when one of these episodes occurs. And you notice that the radio emission sort of stalls at some point and becomes more diffuse, and that will become important shortly. So let's go back to this picture now and ask again, what happens when we want to heat clusters that lie to the right of this line? We can estimate how much energy is transferred in the environment from our simulations, and certainly it confirms that if you just inflate a bubble, it does not provide more than 100% of the energy to explain these systems right here. So how do we then heat clusters with systems where the cavity itself is simply not sufficient? And so we asked ourselves this question, it brought us back to this question of conduction. So this is our picture. Heat conduction has been discarded and discounted because of the large distance between the thermal heat bath and the target gas that is cold that needs to be heated, because this handle is just simply too long. But when we looked at our simulations, we realized that in fact, the jet moves and transports gas of low entropy, low temperature along with it. I'll show you what this looks like in just a second. And that sort of raised a new possibility for how we might heat clusters. So here's a picture of the astronomy department in Madison. I don't know if any of you have been there. It's a beautiful place. If it is not that far, so come and visit sometime. So you can identify the astronomy department by the domes on the ceiling there, on the roof. And there's a little botanical garden just outside. And this is what it looks like in the summer. But when I left, it looked something like this. Well, not quite, but a few days ago it did. And so you must be well familiar with this kind of weather. Madison is further north by 5 hours, so it sees that a lot. And so the winter, is kind of brutal. And you notice that there's snow on the ground, and obviously it sticks there. And yet we have a perfectly good heat source that could, in principle, melt all the snow, and that could heat could heat our astronomy building. Now we just burn fossil fuels. Okay. Talk about carbon footprint, but there's a much better way to do this. And the heat source, does anybody have an idea of what our heat source could be? What's the most efficient way you can heat your house? Solar energy is great, right? Geothermal, right. So yeah, in fact, the combination of the two is what you should be doing. We have a perfectly good heat source, which is just the ground. And it doesn't actually, you don't have to go very far below to see that. So this is a temperature diagram as a function of time of year. Right, so temperature on the x-axis and depth and meters on the y-axis, and that's you notice that the temperature on the surface fluctuates wildly because there's change over the year, but the temperature in the ground stays constant. And so in the winter, the temperature underground is actually nicely suitable for providing lots of heat in there. And then the Earth is big, so there's a lot of heat stored thermally inside the Earth. That we could in principle trap it, yet it doesn't heat the surface because conduction is too slow. And what do? Well,
Drill a hole, right?
you drill a hole, and what do you do then? You pump fluid into the hole, heat it, when it gets close to the heat source, and you bring it back up. That's how geothermal heat pump works. Exactly. Right. So I researched this because in Madison is a really good way to heat your house. So so that's in fact what we propose is happening. So if you can move the cold gas close to the hot gas, or the cold fluid close to the hot fluid, conduction becomes much more efficient. So we have an engine that does this, right? You have to expend energy to do this, right? So the hot fluid, wants to rise, but cold fluid, wants to go down, and so you have to invert this if it's stably stratified. And in fact, clusters are stably stratified. Cold gas is in the center of the gravitational well, and hot gas is on the outside. So to lift cold gas, we have to put energy in. You need an engine, a heat engine, to do that, right? But we do have an engine. Right? It's the black hole in the center that transports first, transports relativistic particles, but then in the wake of these relativistic particles, it turns out that you also lift up cold gas. And in fact, when you inflate the bubble, you lift up cold gas that's the head of the bubble. So I'll show you a different movie of the same simulation. Now, what we call the entropy ratio. So this is the ratio of the entropy in a slice of the simulation at a given time relative to the time when it was unperturbed. Right? So initially, the cluster forget about the black hole in the center, which we cut out of the simulation. That's the cluster ratio. The entropy ratio is 1 because that's the definition of the ratio, right? But when we turn on the jet, initially you inflate these high entropy bubbles, but you also notice that there is cold gas that's being dragged up in the wake of these bubbles. And there's cold gas that's being pushed ahead of the bubbles, right? And so that ends up here. You also end up with an inverted entropy ratio in the center because you've removed cold gas from the center, and something has to go in its place, and that's gas that comes in laterally, which comes from further out in the cluster and has slightly higher entropy. So you've replaced some of the cold gas with slightly warmer gas, and then you've dragged this cold gas to regions where the gas is very hot. And so you've transported cold gas next to hot gas, and that immediately starts conduction, right? Because now you're conducting over a much shorter length scale. And the conduction time goes like the square of the length scale. And so this is much more efficient. So here's the heat flux that we calculate based on this transport. You can see that there's very large heat flux on these large scales. And it's only due to the proximity of the low entropy and high entropy gas. So you can quantify this. And on the left-hand side, I show you these tracer particles that I mentioned, where we embed Lagrangian tracers that track with the fluid or the gas is moving. And this is where it starts in kiloparsecs. So this is the cluster center. And then you go out and you notice that there is some fraction of gas, not a huge fraction, but some fraction of the gas that's transported to larger radii. Right, you can see this over here. So this is where it ends up, and this is where it starts. So anything to the right here is transported outward. On the right side here, there's an actual conductive heating diagram. Right? So what's the conduction doing to different parts of the cluster? And as a function of entropy of the gas. Right? So high entropy gases on the right, low entropy gases on the left. And this is on the y-axis is the position in the cluster. And this is a snapshot. So this is after 300 million years after the jet turns on and then back off. And you notice that uplifted low entropy gas, red, is being heated, right? Red means heating, and blue means cooling, and the high entropy gas that is next to it is cooling. So we see that there is conductive transport, and the conduction, of course, depends on the efficiency through this conduction coefficient, which isn't very well known, right? So your question was, what kind of gas is this? And I'll get back to this in a little bit. So the conduction coefficient isn't super well known, and this is in large part because the gas itself is magnetic. And in magnetic gas, you have anisotropic conduction. And you also have some microphysical instabilities that might affect the rate of conduction. So this is an open question that's an active area of research in plasma physics. What is the conduction coefficient of systems? But for typical conduction coefficients that people assume. So Spitzer rate, which is the classical canonical value, this is 10%, this is 1% of the Spitzer rate, so 100% would be ideal, but this is unlikely to be true. But even in this case, you see that this is the cooling rate. You can see that in large parts of the cluster, you would exceed or at least match the cooling rate. So this seems to work pretty well. And so then the question is, what's the efficiency that your heat pump, if you want to call it that, can achieve in the system? So for efficiency, you have to know how much energy you get and how much energy you have to put in. How much energy you have to put in is simply gravitational energy, right? So you have to do some work to lift low entropy dense gas that is negatively buoyant up above hot gas or in the vicinity of hot gas, and it wants to go back down, right? So you have to do work against gravity. You just calculate the integral of that work, right? And so if you do that, you get this expression here for the thermal energy, for the work you do, sorry, and that's this one here, which is basically Archimedes' principle, right? How much energy you have to invest to lift a bubble or the partial of cold gas. And the thermal energy, that's the energy you gain, right? That's the amount of energy you can extract from the environment. And that depends on the temperature where you raise your plasma to the adiabatic temperature that your plasma has when you put it in that position, right? That's the maximum energy you can get by bringing the plasma that you've lifted into thermal equilibrium with the plasma that is next to it. That's the ideal situation. Of course, it won't happen like that because at some point conduction becomes less efficient when the temperatures are close to each other because it depends on the temperature gradient, but that's the ideal case. And so this depends on the adiabatic temperature gradient, which people working in stars will know well. And because this is a stably stratified system, that adiabatic temperature gradient is positive. So that means that this whole, that reduces that number. Okay, so if you calculate the amount of energy you can extract, divided by the energy you put in, that's your efficiency. Right, so that's plotted here. That's the efficiency factor on the y-axis. This is in a log plot, right? 10 to 0, that's 1. So this is 100% efficiency. So you get the same amount of energy out that you have to put in. And that anything above is more than 100% efficiency. Anything below is, right? And this is the position in the cluster where you take your parcel and put it where you have to put it, right? So if you start, and the different lines are different starting positions. So if you take gas from the center of the cluster, a small radius, okay, and you lift it to anywhere between 0 and 250 kiloparsecs, you can exceed 100% efficiency. So in fact, you get more energy in thermal conduction back out than you have to put in to lift the gas. And that's how a geothermal heat pump works. Right? If you put a heat pump into your house, you get in excess of 100% easily. Right? That's the whole point. Right? If you had less than 100%, it wouldn't be worth doing. So, so the idea here is that by investing a relatively small amount of energy by lifting up this gas, you get a huge amount of energy return. Right? You can easily exceed 100%. And that's really what we need. Right? We need to be able to turn a lot of the energy invested into heat. How much do you get? Right? How hot does the gas actually get? How much temperature difference can you make? That's plotted here. So on the y-axis, on the top panel here, you see the energy gained per particle in keV. Right? That's how we measure temperatures in clusters in keV. So the gas in the center is about between 1 and 2 keV, and the gas on the outside is somewhere between 5 and 7 keV in this cluster. And the maximum energy you can get under 100% efficiency for an optimal efficiency for this process to work is a few keV, and that's exactly what you need. Right? So that really matches the requirements for heating clusters. Okay, so here's a movie that shows this process in a slightly different way. I showed you the entropy ratio. Now I'm going to show you a nice visualization of this that my student Yihao had done a few years ago, now in 3D. And so green is high entropy, blue, purple is low entropy, and you can see this really complicated dynamical structure that evolves out of this over time. And you can clearly see the transport of low entropy gas out in the cluster. And then it just sits there. And eventually it'll come back down. But we don't simulate long enough to really see that happening. But I mean, it looks like a jellyfish, right? And that's because the turbulence and the dynamics behind this are similar. So this is a really promising process. but we haven't finished studying it, obviously. As I said, there are complications. So the next step we're doing is to use full anisotropic conduction to simulate this. Again, I'm using Flash, so we're working with Matthias Ruszkowski, which Mike knows well, in implementing an anisotropic induction network into Flash, and then doing this properly with fully magnetized ISM and everything. So my student Jennifer Stafford is leading those simulations, and we just got a large amount of time from NASA to do this through an ATP, which is really great, and we're very thankful for that. So that's the next step. Stay tuned for that. And I don't know how much time I have.
Yeah, 10 minutes.
10 minutes. All right. So the picture here is, right, we have this mechanism where a radial galaxy inflates bubbles, it lifts up cold gas, that gas gets in thermal contact with the environment, and then eventually, if it doesn't heat completely, it'll come back down, right? If heated at the same temperature as the environment, it'll just stay, but if it's not, then it's negatively buoyant, it will come back down. So there are some predictions that we can derive from all of this. And the first thing that we did was to look at the X-ray emission from these clusters themselves. And you notice here that there is a lot of perturbation to the intensity of this image, right? This AGN does a lot to the center of this cluster. Now it's relaxed on large scales. That means it's dynamically virilized, it's just more or less stationary under static equilibrium. But in the center, there's a lot of churning induced by this AGN. And in fact, my undergrad student, Andrew Heinberg, who's now a grad student in Chicago, analyzed the simulations to compare them to the data. And so what you see on the left here, this is not his image. This is an image by Walker, I believe. This is the same X-ray image of the Perseus cluster, but now a particular kind of unsharp masking mechanism, a Gaussian gradient technique, is applied to the image to bring out ripples and small perturbations, small fluctuations. And you see this beautiful network of waves and fluctuations and just beautiful perturbations. It's one of the most amazing X-ray images I've seen. The fact that you can do this with something that is very low surface brightness is really amazing. So you see that a lot of fluctuations. You can analyze the fluctuations simply taking power spectra. And you can take power spectra in different regions of this image. So there's an annular power spectrum that you can apply to different annuli in the image, and that's shown on the right here. It's a work done by Zhurevlev et al. That shows the power in fluctuations, where you can do this in density perturbation or in velocity space. So they use density as a function of wave number, right? And so small wave number, large wave number. And you see that different annuli, which are sort of listed here in color, right? Small, medium, and larger, 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 larger. You sort of go down, right? So you have a lot of power in the center, and it goes down. And this had a particular shape to the power spectrum, sort of a peak with small wave numbers, and then it sort of falls at large wave numbers. And so we thought, can we reproduce this? Other people have looked at this power spectrum to try to reproduce it with their simulations of other processes. So for example, here's a simulation of an interaction with a companion galaxy group that would fly by, and what they've done is they've sort of looked at the perturbation that you get from a gravitational encounter that induces waves. In fact, that's possibly something that happened in the Perseus cluster, and it matches the larger scale structure quite well. What we've done is we've looked at the perturbations that our simulations of a jet induce in the cluster. And so here you see a similar kind of analysis done to the intensity fluctuations of the cluster gas, and you can see all the ripples and perturbations induced. You notice that here it's really concentrated on the center, and here it's much more diffuse and on larger scales. Right? So these are two complementary processes, where the AGN probably induces a lot of power on small scales, and the large scale dynamics induce power on large scales. And so here are our power spectra as a function of time after the AGN episode. So here's just an image, and that shows the same Gaussian gradient technique. These are different annuli, and for different projections, whether you look down the jet or whether you look perpendicular to the jet. You notice that our simulations produce power that is of the same order of magnitude on small scales, on small annuli, and then on large annuli, it falls away. So we only reproduce the power spectral distribution in sort of the innermost regions of the cluster, which is exactly where the other simulations of the merger and the dynamical interaction don't. So they perfectly match. Here's another way of looking at it. Again, the power spectra overlaid on the observations, where we now tune the power spectrum to try to reproduce what's observed. And it works pretty well, as I said, on the inner sort of 60 kiloparsecs, and further out it doesn't, but that's where the other mechanism kicks in. So together, they seem to reproduce the observed power spectrum. What that means is, if you look at these power spectra, which are the dotted lines here, right? Those are the observations, these are the simulations. The observations of the power spectra actually encode a history of the AGN activity in the center of the cluster. So that's one way to analyze the activity of AGN in the cluster, is to analyze the power spectrum and then try to match it with the history of energy rejection. Okay, so I have 5 more minutes. If there are perturbations induced in the cluster, that should reflect in the turbulence that we see in the gas. And since we can actually look at the emission lines from this X-ray gas, right? This is the iron line, iron K line, for helium-like iron, observed by the Hitomi spacecraft. And it actually is sensitive to motions. Right? I don't know if you know the history of Hitomi. It's pretty tragic. It blew up in space, but it did one observation, and it was at the Perseus cluster. It's very fortuitous. I don't know how much NDK being paid for that, but it was good that they did that, because it measured the width of these lines, and the width of the lines tells you about the turbulent velocity in the cluster. And that's shown on the right here. That's the turbulent velocity on the y-axis here as a function of distance from the center of the cluster. And the measurements are the blue bars, and what's measured is the projected RMS velocity, right? That's what you measure here. That's the bottom plot. And the simulations are the yellow points, and the observations are the blue points. So we're a little below, except that we fall within the error in this region over here. So again, this is a way to constrain the input by AG clusters. Okay, so there's another way to do this, and it's sort of going to be my last short topic here, by looking at the radio emission. So the X-ray intensity encodes, and the spectra encode information about the past history of the AGN. This is a radio image of the Perseus cluster, but on much larger scale. So the radio galaxy I showed you is in here. And so this is now a much larger scale image. And there is in fact a diffuse halo, a mini halo of radio emission from relativistic particles. And the question is, where do these particles come from? There's no good reason for a cluster like that to have a distribution of relativistic electrons in its center by itself. Right? So non-cool core clusters have a good reason, because they've recently been shock heated, and the shock in those clusters naturally accelerates electrons. And we believe that the radio emission from those clusters just comes from the shock. But in this case, there is no good reason for electrons to be there, except, of course, we have a source of relativistic electrons in the center. And so here are 3 different contour maps of this radio halo at different frequencies, 350, 610, and 1400 megahertz, taken by the Very Large Array. And it's a very diffuse region of emission. And so the question then is, we ask ourselves, what can the AGN contribute to this emission? And again, what I show you here is this entropy ratio map, which shows that there's actual transport of gas inward, and then eventually this gas will come back down. Right? The cold gas that was uplifted comes back down because it's still somewhat colder, but when something falls down, right, it produces a draft in its wake, and that will drag some of the radio emission back down. In fact, that's what we see. This is a position velocity diagram for the particles that were now injected by the jet. This is the relativistic plasma as a function of time after the jet turns off. So this is 64, 126, 266, and 500 million years. And this is velocity. Positive means going away from the center. Negative means going down towards the center. And this is radius. So large distance, small distance. And what you see at late times is that there's actually a negative velocity in some of these particles. That means that they're being dragged back down. And we call that a downdraft. And that means that there is actual radio emission. This is the same picture now in radio emission projected, same time steps. where we see at late times is actually radiation emission closer from the center. And that's the opposite effect of the heat pump, right? The cold gas is lifted up and gets heated, but then it has to come back down. And in the process of coming back down, it actually drags down some of the particles, the non-thermal particles with it. So here is what that does to the intensity distribution, or to the emission distribution in synchrotron radiation. These are different times, again, same time steps, young, older, oldest, so 500 million years after the jet episode. It's a long time. And you notice that there is now emission filling in this region that was evacuated at earlier times. And so this downdraft actually produces emission in the cluster center from plasma that was injected a long time ago. So here is a comparison to the actual observations. So this is the average intensity distribution. This is the observation. So we're below a factor of 10 or so at this particular time step. Later on, it becomes dimmer. And that just means that a single episode of AGN injection by itself cannot explain this. But that's not unusual. We know that a single AGN episode cannot explain the history of the cluster, right? Because we have to constantly provide energy for our heat pump, otherwise it doesn't work. We know that there are multiple cavities in the cluster. There's very good evidence that this activity is episodic. And so that suggests that if you have a couple of these episodes, you can actually explain the observed diffuse radiant emission. So again, the diffuse emission in these clusters provides a historical sort of calorimetric view of what happened with the central AGN. All right, so I'm going to put my summary up here and just briefly reinforce that AGN and jets actually mitigate large-scale entropy transport, and that facilitates conduction much more efficiently than it would otherwise occur. That heating is specifically targeted to the lowest entropy gas, which is exactly where you need it. By doing so, you can significantly enhance the efficiency of AGN. You can see the history of AGN injection and the fluctuations in intensity and radio. That's all I have for you today.
I have a question.
Yeah.
And this might be a stupid question, so forgive me if it is. So you have this jet and it's dragging this cold gas out with it, which is interacting with hot gases farther out. Wouldn't you expect like shock ionization and then emission from that interaction of the cold gas and the hot gas far away as
So
it's heated?
if it were not already ionized, yes. Right? And in fact, you do see some shocks that are injected very early on when the jet just turns on, right? So just go back to the Entropy Ratio. Stop this. This is horrible. So if you look at this, right, this is all the non-thermal plasma, but this ridge over here that's bounding it, right, that's actually a shock wave that's driven into the gas. And you can see that in some cases, right? We actually have clusters that do show shock waves. But if you as a heat source, this is really inefficient because a very small fraction of the energy actually goes into that shock. Because as soon as the radio source expands into some reasonably large size, the expansion is so slow that it's no longer that supersonic. And so weak shocks are notoriously inefficient as heat sources. Okay. Yeah, but it's a good question. But the gas is already ionized, right? So it's all fully ionized, at least hydrogen helium, even in the center. Gotcha. Yeah.
I think Jim Buckley online has a question.
Sure. Is he gonna?
Well, he should be able to speak through the, if you don't mute.
Can you hear me? Can you hear me?
Jim, have you unmuted? Yeah, I can't hear you, Jim.
Yeah, I don't think that
Is
it's
it a question about a
working.
gravitational potential well?
Yeah. All right, I'll just read it. What gravitational potential well do you assume around the central jet source? Does the dark matter halo make a difference since it dominates the enclosed mass and gravitational force at some radius? Does this affect the rate that cold gas sinks back down into the core?
Great question. So there are multiple answers to break this apart. So we assume the gravitational potential that's inferred from the Perseus observation. So we can measure, assuming hydrostatic equilibrium, which is not a perfect assumption because we know that in the center there's It's not hydrostatic, but it's the best we can do. So you measure the temperature gradient, you measure the gas density, and together you can get a pressure gradient, and from that you can back out the gravitational potential, just assuming hydrostatic equilibrium. And that's what we assume in the simulations, right? So if there were no jet, this cluster would just sit there and slowly cool. But the question then goes further and, and asks about dark matter. And in fact, most of the gravity in the simulation is dark matter, right? Because that's what the mass density in the cluster is. So on scales much larger than the central black hole, it's all dark matter basically. And so in fact, we don't even do self-gravity. We don't assume that the dark matter is affected by the motion of the gas. And the only way that would happen is if we're the gravitational interaction between the gas and the dark matter. But that's a secondary effect. It's a low order, it's a higher order effect because there's relatively little gas. And so we don't even include self-gravity, we just assume static potential. That's certainly an approximation, but over the time scales of the simulation, it's fine. And then close to the black hole, in principle, of course, the gravity is dominated by the mass of the black hole. And that's not dark matter, as far as we know, other than the fact that it's a black hole. So we call it dark matter, but it's certainly not the same dark matter. But we don't actually simulate the black hole, right? So the simulations we do, I should probably have said that. So the resolution is 30 parsecs, right? And that is already pretty large compared to the black hole. But then, that's just one pixel or one cell. And then, the jet itself is 16 times larger than that. And so on those scales, it's already dominated by other effects. Or it starts to be dominated by other effects. And so we neglect the gravity of the black hole, and we don't actually do any MHD physics of accretion and black hole dynamics in these simulations, A, because they're not relativistic, but B, because it's not necessary, and it's also infeasible, right? Anything that happens in the accretion flow happens on much, 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 much smaller scales, and that's simply not feasible with the dynamic range that we have. So we take the mathematician's approach here and say, suppose the jet exists, and then we follow from there. And that's what people do when they study this, because it's simply not feasible to have 10 orders of magnitude of scale in your simulation. But it's a good question. And if we were to simulate actual accretion and jet acceleration in the vicinity of the black hole, then we would certainly have to include the gravitational potential well of the black hole itself. But overall, it's dark matter. Yeah.
So is there any magic involved in having only one AGN active at a time and being at the center? Or
Well,
is it just...
So, I mean, there is, yeah, certainly it's arbitrary, right? I mean, we only have one injection because the approach we take, and there are two different schools of doing simulations in astronomy, right? You can take the kitchen sink approach and try to do everything, and that's really useful, right? So cosmological simulations try to do that, right? You include every effect in galaxy formation, feedback, stars, everything. But then you have to have a subgrid model for everything, and then you try to reproduce what you observe, and that's really useful for some things, for predicting statistical distributions of galaxies. But it's harder if you want to answer a specific question. So what we look at here is just a simple numerical experiment. Right? We just do a very controlled experiment, and then try to learn from that and apply it. Right? So certainly this is very arbitrary to have one single episode and follow that. Right? What would really happen is that there would be another episode that happens after some time, right? But we don't know exactly what that time is. And so, the next step would then be to say, okay, well, suppose this does happen, we'll do another simulation where the jet fires. And we have those simulations. We haven't analyzed them yet fully. And in fact, we want to wait until we have the fully anisotropic conduction to do that. But I think, just to understand the simple dynamical process of what happens when you inflate a buoyant bubble and you lift gas, this is what you want, right? Because you want to look at a very simple, isolated.
Yeah. No, I guess I meant more in the clusters that we observe.
Oh,
Does it happen that they tend to have an active AGN at the center? Because they could be anywhere.
It's a great question. In fact, there are AGN outside of the center. But the biggest galaxies and clusters are the central galaxies, right? Simply for simple gravitational settling. And so the size of black holes in galaxies correlates with the mass of black holes, and so that's the galaxy with the largest black hole. And in fact, it's sitting in the center of the gravitational well and sitting in the center of the cooling flow where the coldest gas is. And the coldest gas is most efficient and densest, and it's most efficient at accreting. And so that's natural to expect the radial galaxy to be in the center, at least the most powerful. There are other galaxies that have jets. They're not stationary. You can actually see them move through the cluster. is really interesting, but it's not heating the cluster. Right? So it's fortuitous that they are where you need them, but it's not unexpected. The fact that they're all active just tells us that there's a pretty high duty cycle. Right?
So along those lines, do you need intermittency in the AGN jet? Because
It's a good
if
question.
it were just all steady, you'd eventually just push all the cold gas away. So do you need the cycle of allowing it to remix back in and settle back, and then
You don't need
does it become too
intermittency.
uniform and too distributed if you
Well,
have it
we
steady?
haven't done that experiment yet, right? So I can only speculate. So just to give you a perspective on what's expensive and what's cheap in these simulations, it's really expensive to have the jet run them, right? Because the jet is super fast, right? It moves even at just 0.1 c, it's very, very fast. And so the time step of the simulation is inversely proportional to velocity, and you have to have this high resolution all along the jet axis. You don't care about this high resolution everywhere else, but you need it there. And so it's very expensive to run the jet, and it's easy to turn it off and then run it afterwards. So we haven't done it where it just keeps running, at least in the Perseus cluster. We've done it elsewhere, and it does make a difference. Probably what's more important is that eventually it changes direction. Right? Because if it goes and changes direction, then it's essentially like a new outburst. And that does seem to happen. So if we look at these clusters that have connected large-scale radio structures, they're actually, maybe I can show an image. They are really all over the place. Let's see here. So, right, so this one here, MS0735, the jet's going this way, and then before it was going that way. M87, my favorite. My first paper was on M87, so that's this one right here. This has sort of actually been tilted, but the jet is going in this direction, and then radio structures here, and then our large scales is like that. It really does tend to reorient, and whether that is because the jet itself changed direction or because there's large scale sort of rotation or something in the cluster is not clear. But you do need to change direction, otherwise you just eventually, you'll drill a hole, and if you're unlucky, the jet will just dissipate on much larger scales. And this is, in fact, it's an interesting question, right? What do you need for a jet to dissipate in a small enough scale? And remember Jerry Ostraker giving a talk in Madison, he argued against feedback by jets because you can't heat he said you can't heat your room with a laser, right? However, that's only true if the room is optically thin. Right? So as long as you can terminate the jet on the volume that you want to heat, it's fine. And so, so that's what you have to do. You have to be able to terminate the jet. And there are other ways that happens other than reorientation. It could be mass loading, but you do need to drive this large scale circulation on the scales where it matters. So it's a good question, but we don't really know the answer. So I guess that's something we'll have to look at.
And keeping on this slide here, so in your simulations, you have an optimal size for efficiency.
Yeah.
Is there a correlation? Can you translate your simulations for that optimal size to the plot on the right here?
Yeah, that's a great question. There isn't a size scale, but these tend to be bigger the higher you go, just because bigger volume means more energy. All of these systems fall within that size scale, right? But whether that's causation, I would not dare to guess. And it varies from cluster to cluster, right? Because the temperature gradient is different.
Yeah, there's a lot of, it's a long log with a few decks of uncertainty there.
Yep.
You're always trying to, but you do have that nice lump, and it's like you've got that peak there in the middle. I'd be curious whether you can do a normalized version of that correlated with that plot.
That's a good question. You should try that.
Any other questions?
Very interesting talk. So in one of the slides you showed, so you have this energy spectrum, right? And in the center of the mass structures, so it makes sense by this heat pump mechanism. But on the larger scale, you said it's probably because of like cluster merge, right? But I just wonder if there are clusters that you only have, they never experienced any merge, so you can get this clear signature of just this mass structure in center, so you can really see, pinpoint this mechanism. It's not this large scale merging.
That's a great question. So yeah, for Perseus, we actually do, and I'll show you the temperature image where it's a little bit more clear. So you see that there is actually temperature asymmetry, right? Hotter and colder. And that's probably due to some large scale spiral motion. that wasn't a major merger. So it wasn't like a galaxy cluster smashing into another galaxy cluster, which is what you need to really heat the cluster back up, where you just dissipate above the kinetic energy of the cluster and goes back into it. So this is just sort of a flyby. And so it's interesting that this happens in this cluster. It's not present in all clusters. But we also don't have the exquisite data we have yet for Perseus. So it took 4 megaseconds of Chandra, and that is, what is that? That's a month and a half.
Something like that.
And it's a very expensive to run that. And so to get to this level, right? If you were to just look at, and this is the brightest cluster. So it's easiest to do this for Perseus, and it took a month and a half of straight looking at this object. So it's just really hard. But luckily, we have a large telescope that's being built in Europe, but NASA is involved, that will have much more collecting area than Chandra. And so in about 10 years, we should be able to do this measurement in other clusters. So that's the Athena Observatory.
And 20 years of links that are happening.
Yeah, and links will be better, but so what really worries me about Athena is the resolution. You do need resolution to do this. You need angular resolution. You need to see the fine detail, and I think they're going in the wrong direction as far as I can tell. So
Yeah, it's going to be about 8 arc sections.
So the target was 5. Chandra is 0.5, right? So I'm sure that Mike has told you all about Chandra many times, but so each pixel is half an arc second, and the resolution of the telescope is half a second. It's unbelievable. But Athena is going to be an order of magnitude worse at least. And so at some point, you're going to lose the sensitivity to the really small CF distributions. But that's the story. So
It's probably a links, but if links happen,
it's definitely links. Yeah.
It's 25 years from now, but it's hard to make something big in the X-rays with that spatial resolution.
Yes.
So I think there's
If
one
we
last.
had the amount of money that we had for JWST, then it would be fine. But we don't.
One last question from Jim. He wanted to know where the mass is coming from, whether it's the X-ray gas or lensing.
Both. So I mean, the gas mass, it's easy from the X-rays, right? We get the gas mass from the X-rays, but in fact, I mean, we can get the gravitational mass just from hydrostatic equilibrium. So the X-ray measurements are enough to estimate the total gravitational mass.
Any last questions in the audience? If not, let's thank Sebastian.